Okay, we've just talked about the existence and uniqueness theorem for first-order linear differential equations, and we're about to talk about the equivalent theorem for nonlinear differential equations, the existence and uniqueness theorem for first-order nonlinear differential equations. But before we do that, I'd like to talk a little bit about some notation because we're going to see some different notation in that theorem, and I want for those of you who have not seen this notation before to have just a little bit of exposure to it so you know what it means when we get there. I'll refer back to this video from that video, so be aware that that's what I'm talking about. If you choose to skip this video for now, that's absolutely fine. You may not need it. If you've had a course in multivariable calculus, you probably don't need this video, but this is here for those of you who haven't had that exposure. Okay, one thing I'd like to point out is that if we have two functions, f of x and g of x, where g of x is the derivative of f of x, then I just want to make the observation that g of x as a derivative is still a function. So when we get to that part, when I talk about the partial derivative of a function, that is also a function. I'm going to be comparing this to the theorem for linear differential equations. In that theorem, we had two functions, p of t and g of t. In the next theorem, we're going to have two functions, f and the derivative of f. But the derivative of f is still a function. So we're still talking about two functions. Here, I just want to make the point that the derivative is a function. Okay, another thing we want to talk about here is a comparison of what it means to graph some function, let's say x squared plus 1 in two-dimensional space, and what that looks like in three-dimensional space, and why we need to make that distinction, why we need to talk about that now will become clear when we talk about the theorem in the next video. But remember that a function is just a definition. It's just a combination or a list, if you will, of points. It's an infinite list of points in that while it's convenient to talk about x values such as 1 or 2 or -3 or 0, we don't have to use integers here. We can use any real number. So 0.7, the square root of 13, pi, any of those is a valid input for this function. When we graph a function like this, we tend to say, I'll put my chart down here. If x is, then f of x or y is, and we'll say, well, it's -1, 0, 1, and 2. In this case, if x is -1, then I have -1 squared, that's 1. 1 plus 1 is 1. 0 squared plus 1. Oh, 1 plus 1 is 2. Now I can do calculus, but I can't do arithmetic. 1 squared plus 1 is 2. 2 squared plus 1 is 5. So I end up with something that kind of looks like this. -1, 2, 0, 1, 1, 2, 2, 5. And of course, we know this as, I missed that one. We know this as a parabola that's been shifted up 1 unit. I could maybe do that. So this is what it means to graph a function f of x equals, and you're given the definition of the function. And in that case, we say y is equal to f of x. Y, the height of the graph at any given point x, is just a function of the input, right? It's a result of the input, and its behavior is based on the definition here. If instead we are graphing in 3 dimensions, it turns out that what we need is a function, I'll call it g so we can distinguish it from the f in the previous example, and g needs to have 2 input values. And so instead of saying y equals f of x, we say z equals g of x and y. And I'm not going to try to graph a function, but maybe I will. I won't graph a whole function, but I'll define the function so we can try graphing some points. If g of xy is equal to x plus xy plus y squared. Do I want to do that? I don't think I do. I think it's going to get too big if I do that. So we'll just go with that. Then it turns out that each of these points, x comma y, is a point on this plane, on the xy plane. But when I graph it, I'm going to need to find the point on the xy plane, right? Find a point on the xy plane here, and then do this to those values to find the height of the graph over the plane. And that's really hard to graph. It's impossible to graph in 2 dimensions. Well, it's impossible to graph for real in 2 dimensions, but we can take this 2-dimensional screen that I'm working on here, and we can try and use a little artist's perspective to create the illusion of 3 dimensions. If you imagine that this is the corner of a room, this is one wall, this is another wall, and this is the floor. This floor is the xy plane. This is the positive x value, positive x-axis rather. This is the positive y-axis. The negative x-axis goes back here. The negative y-axis is back here. And this is the positive z-axis. The negative z-axis is down here. So we're just imagining that I've taken this coordinate system, I guess, and turned it, spun it around so that the y-axis is pointing off this way, and so that the x-axis is basically coming out of the screen at you, sort of. The z-axis, of course, is pointing straight out of the screen at you in this case, but since we've spun it around, now we can see it, and it goes straight up in this case. So let me start by graphing the function. I'll use, I guess I'll just use white. I'm going to graph the same function over here. In this case, I have x equals -1 and y equals 2. Means I'm over here and up here. So I have a point right about there. And my next point is 0, 1. So I'm where x equals 0, which is right here, and up 1, which is right here. So I'll put a point there. Put some more tick marks on here. My next point was 1, 2, and after that I have 2, 5. So I have 1, 2, I'll have a point about there, and then 2, 5. So 1, 2, and 2, 5, and this looks something like that. And again, if I extend it, I get something like that. So this graph, graphed on the xy plane, where you can see the height of the room, if you will, looks the same. It's just been turned around and reoriented. So that's really what we're after here. This is just the reorientation of the xy plane so that you can see what's happening above it. Now I'm going to erase this graph because I'm going to go back and work with this function here, and this function does not reflect that. So I'm going to erase this graph, and then we'll come back and talk about how to graph a function like this. Okay, that graph is gone, and I've also got rid of a couple of rid of some of the extraneous labels here. I've left a little bit of the negative axes just so that we can continue to orient ourselves. What I'm going to do now is create a chart for myself in the same ways as I would do if I were graphing in Math 98, elementary algebra. If I was just learning how to graph in 2 dimensions, in the same way that I created a chart here, I'm going to create a chart here, only in this case, my input is going to have 2 components. I can choose randomly what values I want for x and what values I want for y. So let's choose 1, 0, 0, 1, and 1, 2 for now. When x is 1 and y is 0, I get 1 plus 1 times 0 plus 0. And that's 1. I should write g of xy up here. In the same way as this is my input column here, and this is my output column, this is my input column for this function, and this is my output column. Now, for my next pair of numbers here, I have x is 0 and y is 1, so I have 0 plus 0 times 1 plus 1, so I have another 1. And then for this one, I have x is 1 and y is 2. So I have 1 plus 1 times 2 plus 2. 1 plus 2 plus 2 is 5. So that's there. That's that value. All right, now I'm going to try to graph these points. First of all, I think I will erase the negative axes because it's going to get in the way of what I'm about to do. I'm going to get rid of that for now. And of course, I erased too much at the last minute there. Here we go. Okay, the point 1 comma 0 is where x is 1 and y is 0. So it's right about, let's use a different color here, right about there. And above that point, I have a height of 1. So I'm going to take that point, and above it, I'm going to plot a point that is 1 unit above that point. So the green point here is just a placeholder to remind me where I am on the xy plane. This value here tells me above this point how far I need to go. 0, 1 is similar. The point 0, 1 is x equals 0, y equals 1. That's there. And above that point, I also need to have a height of 1. Above the point 1, 2, well, let's plot the point 1, 2 first. That's where x equals 1 and y equals 2. So I'm going to go out to x equals 1, and then from there out to y equals 2. So this is my reference point. And above that point, I need to go up 5 units. See, 1, 2, 3, 4, 5. I'm about there. I'm trying to keep my perspective in mind here. Notice that this point straight across the screen here, this point is higher than this one, but that's because the perspective suggests that it's farther back. This one's farther forward 1 unit up, this one's farther back 1 unit up, and so it needs to be higher than it seems like it would. In other words, this one needs to be a little lower. On the z-axis here, 1, 2, 3, 4, 5 is way up here. This point, in fact, I think I might bring it down just even a little bit more, is a little lower than you think it's going to be. Okay, let's just plot maybe a couple more points, just so you get the sense of what's really going on here. I'm going to erase this table, or the entries in the table, I guess. I'll leave the rest, and we'll pick some more points, maybe 2 more. Why don't we try some negative numbers? Let's go with x equals -1 and y equals +1. Let's try x equals 2, y equals -1. And I said 2, that's probably enough. So just the rest is arithmetic. I'm going to take this x value and this y value. X is -1, y is +1, so I have -1 plus -1 times 1, which is -1. That's -2, plus +1. So I have -1 for my result. X equals 2 and y equals -1 gives me 2 plus 2 times -1. That's -2. So these two add up to 0 plus -1. I wasn't trying to get the same value here, but looks like I did. All right, for these ones, we're going to go out to where x equals -1, which is back here a little bit. And then out in this direction to y equals 1, which is about there. Let's do that in green. That's on the floor. And then from there, I need to go down 1 unit. So I'm going to go down, oh, wrong color. I have to go down 1 unit, and so that point is there, below the floor. It's actually a little bit off, but I've kind of run out of room. So for my last point, I have x equals 2, y equals -1. So I'm going to go out to where x equals 2, which is here. Y equals -1. I'm going to go in this direction. So there is so I'm going out to here, basically. There is my reference point, and from there, I'm going to go down 1 unit. Again, that's below the axis there, not on it. Perspective is a funny thing. Anyway, so the green dots are just, they're all on the floor. They're all in the XY plane, and the white dots are however many units they need to be above the floor or below the floor to demonstrate how to graph a function in two variables instead of a function in one variable. Now, why this is important is, well, it's really not, except that we're about to talk now about what it means to take the derivative of a function like this. So I wanted you to see what was going on and understand what this really means, so that when we talk about taking its derivative, you'll know what kind of function we're taking the derivative of. Now, if I graphed a whole bunch more points here, I'd end up with a really nice sort of surface, some kind of swoopy surface over this thing. If you put this into, Desmos can't do it, but there are some 3D graphing, online graphing tools that will do it. If you Google 3D graphing or 3D online grapher, there are lots of tools out there that will let you do this, and you put, some of them ask you to type this in this way, others will ask you to type z equals x squared plus xy plus y, or x plus xy plus y. And when you do that, you'll get a surface, and you'll see these white points are just points on that surface. All right, if you've had Calculus 3 or multivariable calculus, this is probably just review, and it's a fairly basic review as well. If you've passed through that course, then you already understand what's going on here. But if you haven't, then I'm hopeful that this is an orienting explanation of what it means to be a function like this. Okay, I'm going to erase the screen from here down, well, part of it anyway, and then we're going to go back to talking about this function from a different perspective. Okay, I've left both of these functions on the screen because I want to remind you some notation. For example, if I asked you to take the derivative of y with respect to x, I might say it that way. I might write it in that form because this is defined as the function y, but it's also defined as the function f. So I might ask you to take the derivative of f with respect to x, or the derivative with respect to x of the function f. You'll see that both ways. And of course, sometimes we see just y prime. It's possible you might also see this notation, y sub x. Take the derivative of the function y with respect to x, or even f sub x. Take the derivative of f with respect to x. And again, if you've taken multivariable calculus, you've seen all of this weird notation as well. It's in a different context here, but it still applies. We don't usually use this notation in differential calculus and one variable calculus because it's really kind of extraneous. We have enough notation without it, but it does come up in multivariable calculus. So it's kind of good to see it in this context as well. So as far as notation is concerned, you'll see these in single variable calculus. In multivariable calculus, you'll see take the derivative of the function g with respect to x, or take the derivative of the function g with respect to y. You can't do both at the same time, but you can do one or the other. And there are reasons for this, and it's perfectly legitimate only to think of it in terms of either x or y for any particular x or y value. And then when you spread that out across the entire function, across the entire surface, you end up with the information that you need. Again, that's really from Calculus 3. I'm talking about finding the slope in the x direction versus finding the slope of the surface in the y direction. And in order to do this, in order to take these derivatives, we call them partial derivatives. And what we're going to do is we're going to say, to take the derivative of this function g with respect to x, that says that my variable here is x. That's a variable. So in that case, what is y? Well, we're going to treat y like a constant. So if I want to take the derivative of the function g with respect to x, for example, that's going to be the derivative of x, which is 1, plus the derivative of x times a constant. Now, if that was 3x, we'd say, oh, that's just 3. The derivative of 3x is 3. Well, the derivative of yx, then, in that case, is y, because y is a constant. And then plus the derivative of y. But since y is a constant, the derivative of that term is 0. So this is the derivative of the function g with respect to x. With respect to y, I hold x constant. So now y is my variable and y is my variable and x is my constant. So if I take the derivative of this function with respect to y, I get the derivative of a constant, which is 0, plus the derivative of a constant times y, which is just the constant, plus the derivative of y, which is 1. And this is the derivative of g, the function g, with respect to y. So that's the notation that you see, or you're going to see in a minute, in the existence and uniqueness theorem for first-order nonlinear differential equations. We'll talk about it in context in the next video. This is the notation in question here, and this is what it means. It's a partial derivative because I have to take it, I'm only partially taking the derivative here, right? I can only take it with respect to one variable or the other at a time, not both. So it's a partial derivative, and that's what that notation means. Sometimes for this notation, you will also see take the partial derivative with respect to x of the function g, in the same way that you would see that in single variable calculus. You will see that a similar, where is it? Here. You'll see a similar notation here. And we could say g prime, but it isn't specific enough. We can't really use g prime without specifying which variable we want to treat as a variable and which one we're going to use as a constant. So g prime notation doesn't really work in multivariable calculus. I can say take the derivative of g with respect to x, or take the derivative of z with respect to x, or take the derivative of g or z with respect to y. We could talk about second derivatives as well. In this context, I might say y, take the derivative with respect to x, and then take it again. Okay, I'll do it with f. Take the derivative with respect to x, and then do it again. Here, second derivative, I could say take the derivative of g with respect to x, and then take it again with respect to x. Or I could say take it with respect to x, and then the second time take it with respect to y. I could say take the derivative of g with respect to y, and then do the same again, or take it with respect to y, and then turn around and the second time take it with respect to x. That's what second derivative notation looks like in multivariable calculus in this context here. Well, that's what the notation is anyway. We can also use the second derivative of y with respect to x, or the second partial derivative of g with respect to x. But if I want to take the derivative with respect to x and then take it with respect to y, I can't use this notation. I left off a 2 there, left off a superscript. Okay, so this is let me highlight these for you. This is equivalent to the second derivative of g with respect to x is equivalent to this guy right here. You can't use this notation to do mixed derivatives because there's no way to write the superscript. You have to, this is telling me to take it with respect to x, and this is telling me to take it twice, but both times have to be with respect to x. Okay, now that you know what that notation really means, we're going to focus on, in the next video, we're going to focus on this kind of notation, first derivatives only, but they are partial derivatives, and that's what that means. It's the derivative of some function that has more than one variable in it. This one only has one variable in it, x. This function has more than one variable in it, and its derivative has to be taken either with respect to one variable or the other. Once you take that derivative, though, notice that we're left with is another function. Okay, so with that, I'm going to stop this video, and we're going to go talk about the existence and uniqueness theorem for first order nonlinear differential equations. See you there.